Welcome to today's video. Today we're going to talk about the Poincaré Group. Now, this is the first video that can be a little bit dense. It's a relatively high difficulty video compared to the previous ones and compared to the ones that will follow as well. So I would say pay special attention because there's a lot to cover here and it's abstract stuff, okay? And it's gonna be also mostly in covariant form. Let me do a quick summary of what we're gonna see. First of all, we're gonna discuss the difference between active and passive transformations. Then we're gonna talk about the Poincaré Group divided into two subcategories. The Poincaré Group is made of all the transformations that leave the line element invariant. Remember. Now, those transformations, if you remember, were any translations, space-time translations, whether they are time translations or spatial translations, rotations and boosts. And those are associated with changes of inertial reference frame. Okay? The Poincaré Group, we're gonna study separately the translations and the Lorentz group. And we're going to see that in a given frame, you can split translations or space-time translations into spatial displacements and time shifts. But of course, people may disagree on how much something is a displacement, a spatial displacement, or a time shift, depending on the reference frame. Because if you remember in the changes of reference frames through Lorentz boosts, for example, time and space mix. So is that a pure spatial translation? Well, no, for me it's a bit of a time shift and a spatial translation. So they mix and it's difficult to separate them, so we need to consider them together. The same goes, and this might be surprising to some of you, with boosts and rotations. Boosts and rotations you cannot separate when you do relativity. You can in Galilean physics. A boost is completely unrelated to a rotation. We will see that is not the case for the Lorentz group. When you have boosts, as in Lorentz boosts, and rotations, they form a subgroup that cannot be separated into two subgroups or subgroups of rotations and boosts. And that will be very interesting to see as well. Now, before we start, one final thing that I will try to address in this video is a couple of notions that I don't think you may be familiar with if you just follow previous courses. One is this divide. There was a big divide in the way things are presented usually in quantum theory and anything classical. This is a classical mechanics course. It's relativity, but there's nothing quantum about it, right? It's classical in that sense. Classical means not quantum. All right, so typically in quantum mechanics, you're used to using unitary representations of operations of a group. For example, if you do a translation, you write, the unitary that implements the translation is the exponential of minus I h bar alpha p, or something like that, with p is the momentum operator that generates that special translation. Or with spins, right, you do a rotation in the spin space of, again, rotation. We're going to talk a little bit about that, but an operation on a spinner, for example, I can write as minus I, or I don't care about the sign convention for this, h bar, and then some vector a dot sigma, where sigma is the Pauli vector, right? And this Pauli vector is made of three components, sigma 1, sigma 2, sigma 3, right? And they're operators, so you would say they're matrices if you represent them as matrices, and this is the exponential of that matrix. And also we know the commutation relationship between these guys, sigma 1, sigma 2 is minus I, sigma 3, right? And all the others that you can actually summarize very nicely with I, j equals E, I, j, k, sigma k, right? And maybe you don't know what this is, but we will see what this is in this video. This is the Levi-Civita symbol, the fully antisymmetric symbol. We will explain what it is in detail in the middle of this video as well. But you see, there seems to be a bit of a difference. So you would not do something like that in classical mechanics for a translation, right? For a translation in classical mechanics, you do, right, x prime is equal to x plus alpha. And there you go, a translation, right? Well, we're going to see that no, this way of writing things is not quantum. Quantum requires you to write it like that, but you can do it, and we will do it in classical mechanics here. These kind of relationships appear also in classical mechanics. Of course, you're not going to get this guy here, this h bar here, but you can write things like this also in classical mechanics. A self-adjoint representation of the generator of translations, as we do here, is not exclusive of quantum mechanics and doesn't come from quantum. It comes from classical mechanics, you can do it. It comes from the structure of the group of translations, as we will see. Now, finally, one of the things that we will touch on briefly after finishing the Poincaré group, before going to the computer to do some gaming with, to play a little bit with the Lorentz group, is the fact that spin, that thing that you use in quantum mechanics, that thing that was introduced by hand in non-relativistic quantum mechanics when people did Stringer-Lach experiments and saw that electrons seem to have an intrinsic angular momentum, and then we need to update the wave function and consider a spinor instead, that is not quantum. The origin of spin is relativity. And we will see it here. Spin doesn't come from anything intrinsically quantum, although it can, there's something quantum about it in the way it presents in nature, but spin doesn't come from anything quantum, and we're going to see that it actually comes from relativity, or we're going to discuss at least that it comes from relativity. And I hope that this inspires discussion in the in-person sessions. Again, keep in mind that this video will be intense, be prepared for it. Without further ado, let's go and start with the translation group. All right, first let's discuss the difference between an active and a passive transformation, which we can exemplify in the context of the translation group. An active transformation is a transformation that I do to the position 4 vector of some event, right? For example, the event is there, and if it were a rotation, I've rotated this angle. But that is equivalent to doing a passive transformation of the opposite angle on the reference frame. If I carry the reference frame and I rotate like this, the same amount of angle, but with the opposite sign, then my relative position with respect to the event I'm evaluating would be the same. So you can think of an active transformation as displacing the 4 vector by a quantity alpha. As if it's a 4 vector, it's a 4 vectorial quantity. This is a position 4 vector. Let me remind you, x mu is x0, x1, x2, x3. That is, of course, CT, if you want to give it coordinates, space and time, y and z, right? And alpha is just some constant vector with constant entries, alpha 0, alpha 1, alpha 2, alpha 3. Now, the passive one, you displace the origin of coordinates, which is the same as subtracting them. You're right, if you move this like this, and you know this is the origin, and I move this quantity like that, it is the same relative position as if you move the origin like that. The relative position is the same in both cases. Now, this is important to know that an active transformation is the same as a passive transformation with the opposite sign of the parameter, right? But with our loss of generality here, even though the passive transformations are the ones that we consider usually to compute, I'm going to write a plus sign here just because it's nicer, and it doesn't matter because alpha can have, the components of alpha can have any sign, so I can reabsorb any sign in there. All right, so let's consider, this is a translation, right? Let's analyze translations. Now, translations are very easy to write like this in classical mechanics, right? In classical mechanics, you write like that, and then you say, sir, then that means that x prime mu minus x mu, it's equal to alpha mu. Right. Then the one thing I can wonder is that, by the way, I can call this delta x mu, right? The prime, the new one minus the old one, I call it delta x mu, and that's what I call equal to alpha mu. All right. Now, one question I can have is, oh, but you know what I would love? I would love to express this as a linear relation. This is not really, it's an affine relation. It's not some matrix acting on a vector that translates. You're used to matrices acting on vectors to rotate. You may be used to matrix acting on vectors to do boosts, right? But I don't know if you are used to matrix acting on vectors to do translations. Maybe in quantum mechanics you've done it with this unitary representation and self-adjoint representation of the generators, right, that I showed before. But in classical mechanics, I don't know if you've done it. Let's see if we can. The question is there some operator, linear operator actually, let me just write linear. Is there some linear operator O such that I can write x prime mu equals some O hat acting on x mu? Is there such a thing? What we're going to do now is try to find that thing. How are we going to find it? Well, the first thing that I can do is actually write this in power series, in a power expansion. So imagine that I say, oh, I can write the O like this. So x prime mu is going to be equal to, I expand this thing, and it's going to be identity plus the first order term. And this first order term would have, of course, it has to depend on alpha, because alpha is the magnitude of the translation, right? So this O has to depend on alpha. So of course, an expansion on the magnitude of the translation, every term will have to multiply alpha. It's the same as when you have an f of alpha. If you do a series expansion, I'm going to have the f of alpha of 0, if I do it around alpha equals 0, plus f prime of 0 alpha plus f prime prime divided by 2 of 0 alpha squared, and so on and so forth. If you do a Taylor expansion around 0, then similar here, I'm going to get this guy multiplying alpha. So alpha is a 4-vector quantity, and I need a scalar quantity. This thing has no labels, no indices. So the number of indices on the left is 1 mu, on the right is mu. This thing has to have no indices. So let's write a scalar like that. Let's use nu, for example, and then alpha nu. And then, okay, a second order term that is going to be, has 2 indices, so maybe nu and sigma, and then one alpha nu, one alpha sigma, and higher order terms. So what I'm doing here, and then of course multiplying x mu. This is the expansion of the O, and all that I'm doing, this is nothing but a Taylor expansion, a series expansion around 0 of the parameter alpha, when this alpha is a vector. It's a multivariable Taylor expansion, but using index notation to write it very compactly. All right, so let's erase this garbage from here, and let's write it only with the leading order in here explicit. So this is actually equal to identity plus O nu 1, alpha nu, acting on x mu, then plus things that are of order alpha alpha squared. Let's call it alpha nu, alpha mu, alpha nu. Okay? And higher orders. All right, so this thing, let me just write the equation again with the prime here. This is x prime mu equals to the identity operator acting on x mu plus this operator here. Let me write the alpha first. Alpha nu O 1 nu acting on x mu. Plus, of course, things that are of order alpha mu, alpha nu. So this thing is just identity times x mu, is just x mu. I can put the x mu on this side, and that will become x prime mu minus x mu, x prime mu minus x mu, which is what I call delta x mu. So put it on the left-hand side. This term, moving this to the left, I get that delta x mu, it's equal to alpha nu O 1 nu x mu plus things that are of order alpha mu, alpha nu, things of higher order. All right. The next step, what I'm going to do is I'm going to consider an infinitesimally small transformation. Now, what happens in an infinitesimally small transformation? So if I do an infinitesimally small transformation, what I'm applying is a d alpha instead of an alpha mu, right? Alpha mu is the finite transformation. If I do an infinite, again, we're going to learn how to do this more properly when we learn differential geometry. Until then, we need to operate the same way we do in physics courses, which is, let's consider an infinite, a very small, if you don't want to think infinitesimally small, think a very small transformation, the alpha, and of course this delta x mu becomes an dx mu, right? If it's infinitesimally small, infinitesimal transformation. Now, if it's an infinitesimal transformation, the higher order terms here will not contribute. That'll be second order in something infinitesimally small. So what we get here is the leading order term only. We get then assuming, so infinitesimally small translation, so for a differential translation, we get that dx mu, it's equal to d alpha nu O 1 nu x mu. And now I don't have to write the higher order terms because it's infinitesimally small as compared to that. So they need to be differentials of the same order, right? Wonderful. Now, let's consider two things. We have the following two equations here. We have this equation for now, and we have this other equation. We can combine them. So we know that this implies that the alpha mu has to be equal to, so using this equation, has to be equal to the alpha nu O1 nu x mu. Ah, interesting. So this operator has to be, look at this. This is the alpha mu, and this is the alpha nu with some combination with these operators. Now, the only way this can be true is if this thing were what? Pause the video and guess. And then I'll tell you. All right. The only way that this would be true if this were the identity nu mu, right? Because if this is the identity, you get that the alpha nu contracted with the identity, this is a Kronecker delta, so that means that in this sum, only the terms where nu is equal to mu survive, so this thing is the alpha mu. And then the equality would be satisfied. So these equations, these two equations together, imply that O1 nu acting on x mu has to be equal to the delta mu nu. So that will allow us to solve for O1. What could it be? Well, O1 nu has to be a linear operator that acting on this vector here, let's say on this vector here, x0, x1, x2, x3, gives me the delta. What is that operator? We have seen it. We have seen it in the second video. Pause the video again. Guess. All right. So let's see what it is. Remember, if I act with partial mu on x nu, what do I get? Well, I know that this thing would be, well, of course, this thing, if it's partial 3 on x3, remember what this is. This is partial x mu, x nu, right? Certainly, the derivative is a linear operator, so it could be that O is some combination of derivatives. Now, what is the result of that? Well, partial 3x3 is partial x3 of x3. So partial z, that would be 1. And what happens when this is 2 and x3? Well, that would be partial y, which is x2, right, of z, and this is 0. Aha, this thing is exactly the delta mu nu. So, wonderful. The only operator that O1 can be is, the only solution to this equation is that O1 nu is actually partial nu, is the derivative operator. All right, wonderful. So let's erase the garbage and keep going. I don't need to do this, but just to make it nicer later on, and because I want to have some laughs with you about it, let me define an operator. Let me define a differential operator. I'm going to call it P nu, and it's going to be equal to minus I partial nu, that operator there, which means that I can write O nu, which is that thing there, as I P nu, right? All right, I just call it that, and I can actually define it like that, and that means that I can write this equation here, this one right here. I can write a dx mu equal d alpha nu, and then I'm going to put the I at the beginning, I P nu x mu. Wonderful. Now, what does this look like? That looks like a differential equation that you know how to solve. Do you remember? Let me just give you an analogy. Imagine that I have this thing, dx equals I d alpha, I don't know, something p x. And this is a constant, say. And this is x of alpha, right? Which is what you do in a translation. How does the new x prime depend on alpha, right? Give me the initial condition, which means that this for alpha 0, and then for finite alpha, it will be this one. All right, well, if I have to solve this equation, that's easy because I do this, right? If I call this x prime of alpha, and I give you the initial condition that at 0, that thing has to be x, then what is the result that I get? Well, the result that I get would be that x prime would be equal to, again, you integrate this, and you integrate this and get the log. This becomes alpha when you integrate. The log, you take an exponential to undo it, and that becomes the exponential of I p alpha, or alpha p, times x, because that's what happens when alpha is 0. It has to be x. That's what the initial condition. You have an integration constant that is exactly equal to x when it's 0. So you can tell what's going on here. When we solve this differential equation with the initial condition that at alpha 0 the value of the function is x mu, then what we get here is that, let me just erase this and write it here, is that x prime mu is equal to e to the I alpha nu p nu. So this is an inner product, if you want, between the vector alpha and the operator p nu, where p mu, or nu in this case, is defined as minus I partial nu, which is the same as minus I partial x nu, which is suspiciously similar to what you have seen in quantum mechanics. You haven't seen anything relativistic in quantum mechanics, so let's stick to the spatial components. You would have xi here for the position representation, and then p actin, pj, and you would have that this is minus I h bar partial j of xi. This acts on a ket, on a vector of the Hilbert space representing a state of a particle, right? Now you add with that ket psi, you get the wave function psi of x here. You take the derivative with respect to the gradient, right? So this is the gradient of the function. And that is exactly what you get when you apply p to the ket and take the position representation. Acting with p is taking the gradient. Acting with p here is taking the gradient, as you can tell. And the only difference is that here you have an h bar, and here the I is non-optional. Here we can put it in, it's optional. In quantum, for some reason, it's not optional. If you want to know why this is not optional, then take AMATH 474, which is also cross-listed with physics, is the Quantum Theory 3 course that is actually centered in understanding well what it means to get a classical system and quantize it. So I'm not going to get into that. But you can tell that the fact that the momentum is minus I gradient, right, in the position representation is not something from quantum mechanics. This is fully classical mechanics. It's not even relativity, because what I did, I could repeat exactly with the Galilei group, because the translation group is the same in the Poincaré group that it is in the Galilei group. So you can tell here that the momentum operator generating translations and being their derivative with respect to space is not a quantum thing. Also, I mean, this is a Lie group. I can give you the Lie algebra, or in other words, the commutator between all the generators of the group. The generators are these momentum operators, right? And I can write the generators, you know, the commutation relations, p mu, p nu, it's equal to 0. They commute. So all translations commute. This is the same in the Galilei group as it is in the Poincaré group. So translations are not special in relativity. Translations are very similar both in the Galilei group and in the Poincaré group. Now, I hope that this was helpful. Maybe I would recommend that you repeat the whole thing, because this is a very simple calculation with indices and all. And I hope that this illustrates a little bit that having some unitary action, if this is alpha joint, which it is, because it's minus I derivative, minus I gradient, right? If the action of some unitary operator on the 4 vector x mu to translate is not something quantum. It's something that is related to translations and is classical. It doesn't come from the quantum part of it. The only thing that comes from the quantum part of it is this h bar here, and the fact that I need the I in quantum mechanics. And here, I can have it if I want to. There was no need to. I could have just gone with the derivative, right? And have something that didn't have the I in here, still will be unitary. The whole operation, the exponential of an anti-sulfur joint operator is unitary, and that's what we have here. Okay? But this optional I can put in, and it looks exactly like quantum. Nothing special about quantum in that it uses derivatives with respect to space to generate translations. Okay? All right, so this is as much as I will tell you about the translations group. It is a group that I cannot represent with matrices, the generators of the group, the algebra of the group. I cannot represent it with matrices. I need these infinite dimensional operators, which are the derivatives, right? Other than that, there's nothing really super special about the translations group, but I hope that you got the gist of what we did, because we're gonna repeat this for the Lorentz group, this reasoning. And in the Lorentz group, I'm not gonna do all the arithmetics like I did here. The arithmetics are in the notes, and we will also see some of it in the computer. But we're gonna use the same method. All right, let's move to the Lorentz group. Unfortunately, the video was already being too long, so I decided to split it in two,
and the Lorentz group will be addressed in the next video. Until then, see you, take care.